In this brief video, I'll be looking at how an alkene can be formed from the dehydration of an alcohol. The reagents that you need in this particular case are going to be an acid, typically sulfuric acid, which is heated under reflux. The example I'm showing here is a secondary alcohol. Very quickly, just reminding you exactly why this is a secondary alcohol. The carbon with the OH is itself attached to a hydrogen over here. So this carbon is attached to a hydrogen, only one hydrogen, and it's also attached to the OH, so this would be a secondary alcohol. When we are dehydrating this, the important thing to note is that, fair enough, you will actually be eliminating this OH, but in order to make water, you'd have to eliminate H2O, which means with this OH, you also need to eliminate another H, which will come from the adjacent carbon. So it's either going to be this hydrogen, which is going to be eliminated with this OH, or it will be this hydrogen, which will be eliminated with this OH. So there's two ways in which we can actually remove water from this molecule. The first way we can actually remove the molecule is by taking away OH with the hydrogen on the left hand side. The second way to form a water molecule would again be taking away the OH, but this time taking away the hydrogen from the right hand side. So a result of this, you can actually have two different types of products being formed. I'll just label them as blue and red, over here and here. So what we'll be ending up with is either the molecule on the left hand side over here, or the molecule on the right hand side. Now, what I've done so far is only showed you what would happen if the water molecule would be removed from either side, and finally, to complete the picture, if the molecule was released, the water molecule was released from the left hand side, a double bond would actually be formed over here, whereas if it was removed from the alternative side, the double bond would be formed at this location over here. Now that explains exactly how you end up with this particular molecule, which is butene, and this molecule here, which is butanone. And something that I'd like to emphasize over here is that on the one side over here you have a hydrogen and a hydrogen, both of which are on the same carbon of the carbon-carbon double bond, and therefore you will not have EZ isomers. For EZ isomers, you must make sure that you have a different group here and a different group here, and the same situation on this carbon here. Interestingly, let's look at this other side over here now, and if I just highlight some of the areas for you. Looking at the carbon-carbon double bond over here and here now, what you'll be able to see is that the carbon here has a hydrogen group and a methyl group, hydrogen group and a methyl group. So on the two carbons of the double bond, the carbon-carbon bond here has a carbon here with two different groups, and a carbon here with two different groups. So within this molecule, you can have EZ isomers, but you cannot have that situation over here. So different isomers that you can have. If I quickly draw them out, the same molecule as we had on the previous sheet, which was butene. Quickly draw that out. So we had butene, which is this molecule here. To work out the EZ isomers, let's draw the same molecule in a slightly different format. So let's just draw the carbon-carbon double bond, CH3 and H and CH3. I'll try to explain what or how this molecule here matches up with this molecule here. Carbon-carbon double bond is here, which is the carbon-carbon double bond here. This H group is that there. The CH3 here is the CH3. On the other side, the CH here is the CH there. This CH3 is that over there. So this particular isomer is going to be where you have both the hydrogens on the same side. So this molecule would be the Z butene. And the other isomer, if I quickly draw that out, will be in this case what we have is the hydrogen here is different to the CH3 over here, and equally the CH3 here is different to that there. Comparing this molecule with this molecule, both the hydrogens are on the same side, so it's a Z isomer, whereas over here the hydrogens are on the opposite side, and therefore this particular isomer is going to be E butene.